Working problem 13-43 from your textbook. This is a rate law definition problem from initial rate data. Very, very common to see a problem like this in homework and on exams and so on and so forth. It's kind of a classic problem from this kinetics chapter. This particular problem asks us to consider a reaction between nitrogen dioxide gas and fluorine plus a gas phase reaction. This should proceed reasonably fast since we have both gas phase reactants, and fluorine's a pretty reactive substance. To make this molecule, 2 copies of it, 2 copies of this combined with 1 to make 2 copies of that, all in the gas phase. We're given experimental data involving the initial molarities or concentration of our reactant gases, and we're told what the initial rate is. This is an instantaneous initial rate in units of molar per second for the formation of our product. From this information, we want to define a rate law that allows us to describe the instantaneous rate under any series of concentrations. Of course, the trick to doing this is starting with the generic form of a rate law, which I've started to write over here. We write rate equals to something. Okay, now of course, what that something is defines the mathematical relationship. First, we have to write a lowercase k. That's going to be our rate constant for this particular reaction. It's dependent upon the reaction, also the temperature at which the reaction occurs at. We then write a term for a concentration of the reactants. Now, in this particular case, we have 2 reactants. The first reactant is our NO2. It gets its term. And the fluorine gets a term. Square brackets meaning the concentration. Here we're going to treat that as molarity, okay? Now, of course, I'm not done yet. Because our concentration terms in a rate law are raised to an exponent. We call those exponents usually m and n. You can take on a variety of different letters, I suppose, but there's some exponent that we generally need to consider, all right? Now, the exponent might be 0, it might be 1, it might be 2, it can take on non-integer values as well. But the whole idea in this problem is to figure out what those exponents are, what the orders are with respect to each reactant, because of course we call these the orders with respect to the reactant that they correspond to. And then once we do that, we can figure out what K, our rate constant, is, all right? So usually the way I do this is, and most people do it, I think, is you look at the actual experimental data and how changing the conditions of concentration affect the rate. And I basically start off by looking for experimental trials in which the concentration of one of the reactants remains constant and the other concentration changes by some integral multiple. Maybe it's doubling, maybe it's quadrupling, tripling, it could vary, okay? Here, between experiment 1 and experiment 2, we see that the concentration of my NO2 doubles, but the concentration of my fluorine remains the same. The reason why one of them have to stay the same is so that in your rate law relationship, one of these terms remains unchanged. It's a fixed variable between 2 experiments. And that's important. You have to keep one of the variables fixed such that you can see how the other one changes the situation. Okay, so in this experiment, between 1 and 2, if we're comparing them, this will stay the same, which means this mathematically will remain identical. K is going to be identical if we're not changing the reaction, not changing the temperature, which of course we're not. So all of the variables are the same, except I'm changing the concentration of my NO2. I'm doubling it. And in this particular case, if I double my concentration of NO2 from 0.1 to 0.2 molar, it also doubles the rate. Doubles the rate. And again, I know this number is not exactly double this one, okay? If you take the ratio, it should be, what, a little under 2, right? But the thing is that the numbers that they give you for the initial rates, they assume to have some experimental error. And as long as you're close to doubling or tripling, quadrupling, as long as you're very close to that, it's safe to assume that it's quadrupled or tripled or doubled. Okay, so here, this pretty clearly has doubled. So we have a situation where the rate doubled, so this number would double when the concentration of NO2 doubles. That is clearly indicative that my exponent for M is a 1. This reaction is first order with respect to NO2. That characterizes those reactions where you double the concentration, keeping everything else constant, and the rate also doubles. Okay? Oftentimes, that 1 is unwritten. We just include that term in our rate law. Now, I need to do a very similar thing for my fluorine. Okay? So to help me figure out what my exponent n is, I need to look for the case in which I change my concentration of fluorine, but the concentration of NO2 is constant or consistent. And it looks to me like that can be found between these two trials, right? Number 2 and number 3. The concentration of NO2 is 0.2 molar for both of those, so that variable is not changing. But I double the concentration of my fluorine from 2 to 3. Now, what effect does that have on my initial rate? Well, it looks like I also double my initial rate. Right? Again, not a perfect doubling, but close enough within experimental error. So I double my rate when I double my concentration. Again, that is completely consistent with n being equal to 1. Okay, so this is a first order reaction in both reactants. Again, usually not written. It's just an unwritten one. We just include the term. Okay, so if the reaction rate doubles, when you double the concentration, that's a first order process in that reactant. If I double the concentration and then the rate would have quadrupled, that would have been a second order reaction in that particular reactant. If I change the concentration and the rate remains unchanged, then that would be a zero order reaction. Okay, so those are kind of our possibilities that are commonly observed for this determination of rate law. So I've actually made quite a bit of progress, all right? Because now I know that this reaction is first order in NO2. It's also first order in F2. And the reaction is second order overall, because remember you add the exponents together. So second order overall, but it's first order with respect to each reactant. The only thing that's left for me to do here, mathematically, to describe the rate law in very vivid detail, is to solve for this value of k, the rate constant that makes the mathematics work. Now the way that you do that is after you figure out what the orders are, the m and the n, you basically come back and use experimental data, plug in experimental data into the equation that you got to rearrange and solve for k. All right, so that's basically what we're going to do. So I imagine I could just use this first trial here to kind of keep things simple and say that my reaction rate that was observed, my instantaneous rate was 0.026 molar per second, moles per liter per second, and that's got to be equal to k, my rate constant, times my concentration of NO2, which in that trial was 0.1. I'm going to write that in for 0.1 moles per liter times 0.1 moles per liter, because that's my concentration of the fluorine in that experiment as well. Okay, so this is now a valid equation that I can, of course, rearrange and solve. If I do that, the number that I get on my calculator is 2.6, okay? The next thing that I need to consider is what is going to be the units of measure for that k. The units of measure that are associated with our rate constant of reactions, it turns out it's going to change depending on the overall order of the reaction. Okay? The reason why that is because ultimately our rate is going to be measured in concentration change per unit time, here molar per second. Okay? If I start squaring things or raising things to the third power over here, the units of measure for k are going to have to correspondingly change to make my rate work out to consistent unit. Okay, so basically, I mean, you can memorize the units for overall first, second, third order reactions. Usually, what I just try to do is to figure out what units of measure are going to kind of be consistent to work to give me the observable rate units that I have in my problem. So here I have molar per second as my desired unit of measure for my rate. And if I look over on the right-hand side, I've got molar here and molar here. It's kind of like molar squared or molar times molar, right? So I'm going to have to get rid of one of those functionally, right, by canceling them out mathematically, which means I'm going to have 1 over molar for a unit here So when I'm doing the multiplication, one of them go away, I have one left. Hence I've got this, and it's consistent. And I'm also going to need to add a second term, and generally you're going to have a time term in your rate constant K per second. So here, that's all I just need is per second, and the units work out fine. So that is the rate constant for this reaction at this particular temperature. And this demonstrates problem 13-43. It's first order in both reactants, second order overall.